Okay, this video is a demonstration, a little discussion on how to use a normal distribution, bell-shaped, right? Bell-shaped distribution to approximate a binomial probability distribution. Now this is kind of strange because I've got two things going on here. So far, a normal distribution, as you might have seen on some of my previous videos, is really dealing with continuous data, right? Anything that can be measured. Whereas a binomial probability distribution, binomial data, is mostly discrete data, almost entirely discrete. And so I'm going to try to use a normal distribution that really deals with continuous data to approximate, it's not going to be exact, but it's going to be pretty close, a binomial probability distribution, which is discrete data. That's kind of interesting, but let me do a real quick recap of what I mean by binomial probability distribution. First of all, I have a number of trials. That's what little n is, number of trials. I have an x. X is the number of successes, right? The number of successes that I've had given the number of trials, n, and x cannot be any number greater than n. Okay, so x is restricted by n. I also have little p, which is the probability of success, and I also have its complement, little q, probability of failure. Okay. The other thing too that you might recall from a binomial probability distribution is if you know these values, n, x, p, and q, you can find the mean as well as the standard deviation. Right? The mean formula is really simple. It's just n times p. That's how you find the mean. You take the number of trials times the probability of success. That will give you the average, the population mean. And the standard deviation, well, that's a little bit deeper. It's actually n times p times q. Right? You can multiply these three things, the number of trials, the probability of success, and the probability of failure, and then square root that value. Alright, so that's just a quick recap of binomial probability distributions. Now, how do we use a norm dist to approximate this? Well, before I get into that, I've got to tell you about two little caveats, two little things that we have to make sure are true, or else if these things are not true, we cannot do what we're about to do here. And I'm going to go into a couple of examples in just a second here. But the first thing is that you have to keep in mind is that I want to check, right? So we're going to put all this here as a little check. We're going to check two things here. We're going to check and make sure that n times p, really that the mean, right? N times p is also known as the mean. We're going to make sure that n times p is greater than or equal to 5. Okay, that's one of the checks that we're going to do. We're also going to check that n times q, the probability of failure, is also greater than or equal to 5. Now, if either one of these two products is not true, right, it's not greater than 5, then we're going to stop right there and we say we cannot do this, right? We cannot use the normal distribution to approximate binomial probability distributions. So both of these products must be true, and I hope you see that this is really just the mean, isn't it? Look at that, it's just the mean. Okay? Okay, so these two things have to be true for me to use norm s dist. The other thing too that has to come into play here is this concept called continuity correction. Okay, so assuming that these are true, that these products are greater than or equal to 5, I also have to use this other idea called a continuity correction. Okay, this is an interesting concept, because what this continuity correction is all about is taking a discrete data value, right? It's taking a discrete data value and turning it into kind of a continuous data value, right? It's turning a discrete data value into a continuous data value. What do I mean by that? Well, take a look at this, for example. If I'm interested in the probability of an exact number, let's use like 8 for example, right? If I'm interested in what's the probability of that exact number coming up, well, continuity correction says, okay, that's too discrete for me because the area of this little skinny line is actually just 0. So what I'm going to do is I'm going to move to the right of it just a little bit and to the left of it just a little bit. And what I mean by just a little bit is, by convention, we're actually going to use 0.5. So just to the right of 8 is 8.5, and just to the left of 8 is 7.5. So what I'm actually going to do, this is how continuity correction works, is I'm actually going to find this shaded area in between 7.5 and 8.5. Alright, those are the values that I'm going to be interested in. That is, again, if I was only looking for the probability that x was equal to exactly 8. Right? Let's try out something else here. We're going to come back to these numbers here in just a bit later on. But how does continuity correction work for, say, something like, how about this? X is greater than or equal to 8. You can see on a previous video that I've recorded that this corresponds to at least 8. Right, at least 8, where we include 8. Well, picture-wise, all right, picture-wise, let's say that 8 is sitting right there. If I want to include 8, and I'm going to shade to the right of it, I hope you see that's a shading to the right there, then if I want to include 8, I need to go just to the left of 8, which is 7.5, okay, just shy of 8 on the left side of it, and I'm going to shade everything greater than that. Right, because that is a greater than symbol. That's what at least 8 looks like as far as continuity correction is concerned. Right, as far as continuity correction is concerned, I'm actually going to look up this. Okay. Let's see. How about at most 8? How about that? At most 8. At most 8 also includes 8. Again, you can look this up on a previous video that I've recorded, but at most 8 looks something like this. Let's say 8 is over here. At most 8 includes 8, but it's shaded to the left. All right, it's shaded to the left, which means that if I want to include 8, then I'm going to peg, right, just go a little bit above 8, which is 8.5, and at most 8 means I'm now going to shade all of this area over here. Okay, this is what at most 8 looks like. Right? So continuity correction says this. That's what I'm going to look up. Now, everything that I've shown you so far, right, these two examples that I'm showing you right here, and the one that I did on the previous sheet, and I can bring that back up. Do you notice that all of these numbers here, right, especially these two right here, continuity correction, are x values. Okay, these are x values. Same thing here with this one. Look at this, right? These are x values right here. Right, these two numbers are x values. How do we change x values into a z value? Because I can't just look up something like this. I can't just look up something like this in a normal distribution table. I can't look up an 8.5 x value. I have to change those into z values, and that's the last thing I'm going to show you in this video here. So we have a nice simple formula. Perhaps you're used to seeing this by now, and if not, this is what it looks like. If you want to change x values into a z value, it's this nice simple little formula, and it looks like this. Z is equal to x minus the mean divided by the standard deviation. Right? So if I plug in any x value that you give to me, and I subtract the mean, divide by the standard deviation, it will change that x into a z value. Now, where are these two things coming from for our binomial probability distributions? Well, remember what I showed you at the very beginning of this video, that, bring that back up here so you can see it, that we can find the mean and we can find the standard deviation given n and p and q. All right, so we can find these values, the mean and the standard deviation, by n and p, or the square root of npq. That gives us standard deviation. Now remember, you can only do what I'm showing you here. You can only use this thing if, right, using this little caveat here, you got to make sure that both n and p are greater than or equal to 5, and n times q greater than or equal to 5, right? So this product and this product are both, right, I'll put you here, both must be true. Not just one of them, but both of them must be true. All right, hope that helps.